Hello. In today's session, we are going to prove theorem 1.4 in chapter 4 about complex integration. And we had started with the definitions of bounded variation and total variation of a function. And also, we had discussed about how a piecewise smooth function can be associated with bounded variation and how to calculate the total variation of the same function. So, in this theorem, we can see the statement to be given a function gamma which is of bounded variation, and suppose we are knowing that a function f is a continuous function from the closed interval a b to c, then we are able to find a complex number I such that whenever epsilon is greater than 0, we can find a delta greater than 0 such that the partition P is equal to the set T0, T1, etc. Tm with the norm of P is equal to the maximum of Tk minus Tk minus 1. That means it is the maximum of the lengths of the subintervals of P, and that norm is strictly less than delta, then if this happens, then the modulus of that complex number minus the sum sitting here, summation k is equal to 1 to m f of tau k into gamma of tk minus gamma of tk minus 1 is strictly less than epsilon, and these tau k's are coming from the subinterval tk minus 1 less than or equal to tau k less than or equal to tk. So this is the statement. Even though it seems to be little lengthy, it is we can split them into part by part and understand it very nicely. Okay, and in this theorem there is also a important remark, and that is a definition. You can see the definition here. Okay, the definition says this number I which satisfies this property is called the integral of f with respect to gamma over closed interval AB, and it is denoted by I is equal to integral from a to b f of d gamma, which is equal to integral from a to b f of t d of gamma of t. Okay, so what this theorem actually gives us, the implication is that we are defining the integral of a function with respect to a function, and this function you usually denote it by some path. Okay, if this is some path, we are actually defining an integral. Okay, so and we are saying how we can define that integral, how this integral come into picture. Okay, so let's see how we can prove the same. Okay, so hope you understood that if we have such an I which is satisfying this inequality here, we call that I as the integral of f with respect to the gamma sitting here. Okay, so whenever you are asked this question, how can you define the integral of f with respect to gamma, it's better to acknowledge the statement sitting here and then write what the integral is denoted as. Okay, so let's move on to the proof. So as the first statement, we can say in the proof that we have our f to be a continuous function. It's given in the statement of the theorem, and this continuous function is having the domain closed interval ab, which is a compact set in the real line, right? So f is a continuous function defined on a compact set, and that means f is uniformly continuous. Okay, so what can we do? Okay, by the property we are knowing that f is uniformly continuous, we can say that whenever we have epsilon is equal to 1 by m strictly greater than 0, you will be able to find delta such that modulus of s minus t is strictly less than delta will imply modulus of f of s minus f of t is strictly less than 1 by m. Just leave this 1 by m part. See, suppose if I am having it to be, see, this is epsilon and this is delta. Okay, so this is what we are saying. F is uniformly continuous. That means for every epsilon greater than 0, we are able to find a delta greater than 0 such that whenever modulus of s minus t is strictly less than delta, we will have modulus of f of s minus f of t is strictly less than epsilon. That is what uniform continuity of f will make us understand, right? So for every 1 by m, consider epsilon m to be 1 by m. Okay, so whenever this epsilon m is strictly greater than 0, we can find a delta m corresponding to that, such that whenever modulus of s minus t is strictly less than delta m, we are going to get that modulus of f of s minus f of t is strictly less than epsilon m, which is equal to 1 by m. That is what is written here. See, if modulus of s minus t is strictly less than delta m, then modulus of f of s minus f of t is strictly less than 1 by m. Okay, and also you are given a peculiar aspect there that we can inductively find positive numbers, delta 1, delta 2, delta 3 correspondingly, such that delta 1 is strictly greater than delta 2, strictly greater than delta 3, strictly greater than delta 4, and so on, that we can find. So what did we just conclude here? See, epsilon m is equal to 1 by m, then we can find a corresponding delta m. Just think about the epsilon delta game. If you have an epsilon, then you can find a delta. So when it is 1 by 1, we denote it as delta 1, 1 by 2, we denote it as delta 2, 1 by 3, we denote it as delta 3, and so on. So for every epsilon m, we can find a delta m such that delta 1 is strictly greater than delta 2, strictly greater than delta 3, such that they satisfy the condition we just said. Now, for every m greater than or equal to 1, m is obviously coming from natural numbers. Okay, say, okay, let script p suffix m is equal to the collection of all partitions p of closed interval ab such that the norm of p is strictly less than delta m. We know for an m you definitely have epsilon is equal to 1 by m, epsilon m is equal to 1 by m, then you have a delta m. So what we are going to do, we are, if we are fixing script pm, we are collecting all the partitions possible on closed interval ab such that the norm is strictly less than delta m. Note that what is norm? Norm of the partition p will be the maximum of the length of the subintervals of that partition. Okay, so that is how we define script PM. And definitely script P1 will be superset of script P2 will superset of script P2, superset of so on. Why? Because we earlier said that we are inductively finding positive numbers delta 1 strictly greater than delta 2, strictly greater than delta 3, and so on. So that is actually helping us to conclude that the partitions are being moving like this one. Okay, fine. Now we are going to define a set. Okay, the set is called fm, capital Fm. Okay, and this fm is defined as fm is equal to closure of. So that means closure means you have a bar like this. Okay, it's written already closure. That means it is a bar of set summation k is equal to 1 to n f of tau k into gamma of tk minus gamma of tk minus 1. P is coming from script pm and tau k is in between tk minus 1 and tk. So note that this function, this summation is nothing but the summation which is coming in the statement here, I minus this summation, the same summation we are using in the set. And the uh, P partition is varying from the collection of all partitions we just mentioned earlier, script PM, and OK is coming from this, the same. Now we have two claims. Okay. Yes, to understand it a little bit more properly, we have for each delta n, we can find script PM and delta 1. If you have a delta 1, you can have the collection of all partitions whose norm is strictly less than delta 1 coming under the set script P1. And delta 2, you will have script P2 and so on. And what we said now here is script P1 is superset of script P2, superset of script P3, etc. Going on like that because delta 1 is strictly greater than delta 2, strictly greater than delta 3 and so on. Okay. Okay, now you have two claims to prove. Okay, the first claim is that what we defined now, the FMs, they are in the decreasing order of containment. That is F1 is superset of F2, superset of F3 and so on. And the diameter of Fm is less than or equal to 2 by m into capital V of gamma. Capital V of gamma is nothing but the total variation of the function gamma. Already said that this gamma is a bounded variation. Okay, so note that the diameter of a set is nothing but the, if you are taking the modulus of all the differences between 2 points in this FM, okay, take the maximum possible of such differences, the modulus of such different differences, that will be called the diameter. So if we are proving these two uh, statements, that is this claim, let's see how we can manage to move on in the proof. Okay, suppose if we prove this claim, suppose assume that the first and the second statement is proved. Okay, so from this chain and from this, we know that the diameter of each of the if diameter of f1 will be, if this is so, we know the diameter of f1 will be less than or equal to 2 into v of gamma, and then diameter of f2 will be 2 by 2 into v of gamma. That means diameter of f2 is less than or equal to v of gamma, and then diameter of f3 will be less than or equal to 2 by 3 v of gamma. So that means the each of the diameter is decreasing as such, and they are uh, a decreasing chain, right? So by Cantor's theorem, just for simplicity, just look here. You're having F1 here. Suppose F1 is here, F2 is here, F3 is here, and it is going on like that, right? By Cantor's theorem, we say that if this is moving on like that and the diameter is decreasing, we know there will come a common point for all these FMs, okay? And that point is called let's say I, it is a complex number I that happens to be in Fm for every m. Okay, that is what Cantor's theorem says. So if we prove the first statement, you get a complex number I in Fm for every m greater than or equal to 1. Okay, so if it is so, let's assuming that both of the statements are true, we are going to say that if we claim, if we prove the claim we are mentioning, we can end our proof in some way. Okay, see, suppose if both are true and if epsilon is greater than 0, let m greater than, strictly greater than 2 by epsilon into v of gamma. Okay, we have an epsilon greater than 0 and let m be some number which is strictly greater than 2 by epsilon into v of gamma. Okay, then rearranging, you get epsilon is strictly greater than 2 by m into v of gamma, right? And we assumed, we are claiming that this is true, right? So that means this 2 by m into v of gamma is greater than or equal to diameter of fm, right? So what we now got is epsilon is strictly greater than diameter of fm. Okay, so if epsilon is strictly greater than diameter of fm, and we are saying that in fm this complex number I is occurring, right? So if you're considering the open ball which is centered at I, this complex number I with the radius epsilon, we definitely know that fm will be contained in that open ball, right? Okay, so just for instance, what we just now said is, see if this is fm. Okay, what did we just say? We said that the diameter of fm, the maximum possible uh, value between 2 points, mm, will be definitely, if this is the diameter of fm, that will be strictly less than epsilon. That's what we said, right? So what we are just saying is this I happens to be inside this fm, right? So if this is epsilon and we are drawing the open ball centered at I, um, and if this is bi of epsilon, definitely this fm will be contained in bi of epsilon. That's what we just said now. Okay, so this means that whenever delta is happening to be delta m, okay, delta and delta m, right? Then our theorem is proved, because this I is happening inside, see, I is inside rfm, this I, then this I is inside rfm, and this particular value is happening inside fm, right? And since this I and this value will be lying inside the epsilon ball with center I, the modulus of that will be strictly less than epsilon. That's the logic there. Okay. So if we claim these two statements, we will complete the proof. That's what we are aiming at. Okay. And also there is some more things to note. Uh, so how we'll prove this f1 is superset of f2 superset of etc.? That obviously will follow from the partitions, the collection of partitions being superset of uh, script p1 superset of script p2 superset of etc. Okay, why? We already know that the collection of partitions have the property this, right? And from that we are taking p's, right? And this is being defined. So definitely fms will also have the corresponding property like this. Okay, so the first claim is very trivial, and for proving the next one, what we are going to do is we are going to take 2 points from this fm and take their modulus, and we say that those two arbitrary points will have the modulus of that will to be less than or equal to 2 by m into v of gamma. Okay, so we are going to do that. Okay, so first what we are going to do is, for this sum, okay, this sum will be called sum s of p. Okay, and similarly another sum is s of q, and we are going to say that modulus of s of p minus s of q will be less than or equal to 2 by m into v of gamma. So definitely diameter will be less than or equal to 2 by m into v of gamma. So for that, we are considering a partition P. We are going to do the idea which we mentioned now. Okay, we have a partition P which is T0, T1, T2, etc. Tn. Okay, and we are going to denote S of P to be equal to the sum sitting here. This sum is nothing but the sum which we are requiring in the statement of the theorem. Okay. Summation f of tau k into gamma of tk minus gamma of tk minus 1, where tau k is happening from the subinterval, closed interval tk minus 1 and tk. Fine. So it is called S of P. Now we are going to fix an m greater than or equal to 1. And we are taking a P from script P M. From the collection of all partitions, we are going to take a P. That means norm of P will be less than or equal to delta M by our definition. Okay, we are having lot of partitions, script P1's collection of partitions, P1, P2, P3, etc. We are going to select one among them, script PM, by fixing the M. Okay. Now our first step is to show the claim. The claim is whenever P subset of Q, then modulus of S of P minus modulus of S of Q is strictly less than 1 by M into V of gamma. Okay. So here we are saying P is subset of Q. So for our easiness, we are going to prove that P is subset of P union just a point. Okay. We are giving the proof outline of the proof for that, and the rest will follow from there. Okay. So let this Q, this Q in the assumption is equal to P union a point T dash. Okay, that is equal to Q. Definitely P subset of Q, right? So how did we obtain Q? We obtained Q by adding one extra partition point to P. That simply means that we know that P is equal to T naught strictly less than T1, strictly less than T2, etc., strictly less than Tn, right? So what we are going to do is nothing but if this P already had partition points TP minus 1 and TP, we are introducing just one more point inside this uh, TP and TP minus 1 and TP. So we are calling it T dash. See, this T dash is the extra partition point of Q. Definitely P, the partition P is contained inside Q. That is very obvious. Now, and so we have two extra subintervals coming here, right? The subintervals will be this one, the closed interval TP minus 1 T dash, call it T star, okay, and uh, closed interval T star TP. So in that subintervals, we are going to select a sigma and sigma dash. Fine. So we define a sum as S of P sitting here. So we are going to find what is S of Q. So S of Q is equal to the same sitting here, right? So since it is Q, I am going to, instead of tau k, I am going to take sigma k from each of the subintervals. So from the definition, we know that tau k is coming from the subinterval tk minus 1 and tk. Since we are considering a new partition Q, this tk might be different. How tau k minus tau k will be different uh, for this Q. So I'm going to choose it as sigma k. Okay. And there is also a different difference. We had introduced a new partition point. So we have to take that into consideration. So what we do is I'm going to uh, not consider that P minus 1 and P here. So rest of them is here. Okay. F of sigma k into gamma of tk minus gamma of tk minus 1. Plus then we are going to consider the partition T star, the subinterval, closed interval T star and T star comma TP minus 1. And from that interval, we had suggested the point sigma. So we are taking it to be plus f of sigma into gamma of T star minus gamma of TP minus 1, extra first term, plus f of sigma dash into gamma of TP minus gamma of T star. Okay, that is very simple from there. So note that this first, the one term here and the second term here, the extra terms are coming just because we had added one more partition point to the partition P for Q, right? Now, we are going to use the fact that whenever modulus of T minus sigma is strictly less than gamma sigma m, delta m, we have modulus of f of tau minus f of sigma to be strictly less than 1 by m, right? Why? Because f is uniformly continuous from our first inference, right? So now we are going to find the modulus of s of p minus s of q. So for that, we are going to write s of p, that is equal to modulus of s of p. S of how did we rearrange s of p is that S of P will be like this, right? Summation, if I am writing K not equal to P, I'm going to just make the P out because P is where the partition P and partition Q are making the difference, right? So modulus of summation K not equal to P F of tau K into gamma of Tk minus gamma of Tk minus 1 plus f of tau p into gamma of Tp minus gamma of Tp minus 1. So that ends S of P minus S of Q. So when we rearrange them, what we can do is the term sitting here and the term sitting here can be arranged like this. Summation K not equal to P f of tau K minus f of sigma K into gamma of Tk minus gamma of Tk minus 1. Then plus this term, the extra term which is coming out from S of P minus the terms sitting here, the term here and the term here. So that's how we are end up there. And then what we can do, then we can take the modular sign inside and make it as an inequality. Hmm. And then modulus of f of t tau k minus f of sigma k, that will be strictly less than 1 by m, right? Because modulus of tau k minus sigma k will be strictly less than delta m. That will make us understand that the corresponding modulus of f of tau k minus f of sigma k will be strictly less than 1 by m. So here we can substitute the modulus of that with less than or equal to 1 by m for for each of the term, and you can take that out. Plus what we can do is we can add uh, plus f of tau p into gamma of t star minus f of tau p into gamma of t star, and then rearrange within the braces to get the terms sitting here. Okay. Also, you can observe that this topi and sigma are coming from the partition which is in from the collection of script PM. So modulus of TP minus gamma will be strictly less than delta m for sure. That means that modulus of f of topi minus f of sigma will be strictly less than 1 by m there also. And also here modulus of Tp minus sigma dash will also definitely be strictly less than delta m. That means modulus of f of 2p minus f of sigma m will be strictly less than 1 by m there also. So you get the inequality happening like this. And when we are rearranging and opening the braces, you get like this. And this is less than or equal to 1 by m into v of gamma, because v of gamma is nothing but the supremum of uh, all the values sitting here. So modulus of s of p minus s of q is less than or equal to 1 by m into v of gamma. So the claim we just mentioned is proved because we added for Q just extra one partition point to P. So even if Q contains more than one partition point, then how we moved the proof? In the same manner, we can prove that also. So we just proved our claim that if P is subset of Q, then modulus of S of P minus S of Q is strictly less than 1 by M into V of gamma. So that is proved there. Now, to end up, you can say that in the second in the second stage, suppose if P and R be any two partitions in script PM, okay, definitely their norms will be strictly less than 1 by M, okay. Then the Q, which is defined as P union R, is a partition. That is also a partition and definitely contains both P and Q. And using the first part which we now proved, we know that modulus of S of P minus S of R is less than or equal to modulus of S of P minus S of R. We are going to add and subtract plus S of Q and minus S of Q, and then use a triangle inequality to get that to be less than or equal to modulus of S of P minus S of Q plus modulus of S of Q minus S of R, and that is less than or equal to 1 by m into v of gamma plus 1 by m into v of gamma, that is equal to 2 by m into v of gamma, right? So it follows that the diameter will be less than or equal to 2 by m into v of gamma. So this is theorem 1.4, which helps us to define the integral of a function f with respect to a function which is of bounded variation, right? So this is the main section of this theorem, that is integral of f with respect to gamma, which where gamma is a bounded variation. So that's all for today. Thank you for watching this video and hope you can link the logical lines as we move in the proof, uh, and do make out your lecture notes. Thank you so much.